The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Reaction below at 925 Kelvin in a 6-liter reaction vessel, what is the equilibrium constant for partial pressures when there is 0.08 moles of sulfur trioxide initially present, and at equilibrium the sulfur trioxide, the amount that we have is 0.0612 moles. Okay, great. To find the equilibrium constant for partial pressures, we can find it from the equilibrium constant for concentrations, and we can relate it through the equation that we just learned in the lecture preceding this one. And in order to find our equilibrium constant expression, our equilibrium constant for concentrations, we can just do so from the equilibrium concentration from our ICE chart. Wonderful, so let's go ahead and get started with that. If we look at a reaction here, is it balanced? That's what we always need to check first. Yes, our reaction here is balanced. Wonderful. So let's go ahead and write it down. So we now have 2 moles of SO3 gas converting to give us 2 moles of SO2 gas plus oxygen gas. Great. Additionally, because our equilibrium data is given to us in moles, we can go ahead now and demonstrate how to work the ICE table with moles. Typically, if you're given equilibrium data in moles or partial pressures, you'll work through your ICE table in however the data is given to you. Okay, great. So our initial concentration here, sulfur trioxide, they tell us is going to be 0.0800. And we also know the amount of sulfur trioxide present at equilibrium. That's going to be 0.0612. Now, how do we find the change? Well, we can just take our, so the change, right, is going to be, oh, and also we don't really have any sulfur dioxide or oxygen present initially. The change, we were saying, is just going to be our equilibrium concentration, which is 0.0612, minus our initial concentration, which is, I got ahead of myself there, it's just going to be 0.0800. This is going to give us a value of negative 0.0188. So if this value here now is 0.0188. Wonderful. Now to write down the change for our products, we have to take note of one thing. We see here that we initially have 2 moles of sulfur trioxide. Here we have 2 moles of sulfur dioxide, and we have a mole of oxygen. So the change for 2 moles of sulfur trioxide to 2 moles of sulfur dioxide is going to be exactly the same as the change here. So we can go ahead and just write down 0.0188. But now, because we're going from 2 moles, right, to a single mole for the oxygen, it's going to be half that amount, the change. Therefore, we would then write down 0.0094. Okay, great. And now at the equilibrium concentration, this is going to be 0.0188, 0.0094. Wonderful. Okay, great. Let's actually now continue with our problem here on the next slide, where we can convert. Oh, I should have wrote this in as well. So we're working here with moles, working here with moles, working here with moles, right? So now what we can do is Go to our next slide. We'll change our equilibrium concentrations from moles to its molarity, and then once we have the molarities at equilibrium, we can find the equilibrium constant for concentrations. And once we find the equilibrium constant for concentrations, we can then relate that to the equilibrium constant for partial pressures. Wonderful. Okay, we'll begin here with a sulfur trioxide, which we see as 0.0612 moles over, remember we said that we had 6 liters. We go back, we were told that in a 6-liter reaction vessel, that's where I'm getting this 6 from now. 6 liters, once you go ahead and you do the math on that, you're going to end up with a value of 1.02 times 10 to the power of -2 molarity. Wonderful. Now we can do the same for the sulfur dioxide.